Let's talk about percentages. In this, we will talk about converting between fractions, decimals, and percentages, computing and interpreting percentage and percent change in the context of a situation too. Okay, let's begin with the base 10 place values system. Let's go, I'm going to draw this out here. Let's go 1, 2, 3, 4 at least. And then let's do 4 on this side too of the decimal. Okay, so let's see. Keeping track. So here we have the decimal. So this would be our ones place. Counting to tens because we have 10 fingers, literally 10 digits. And then 10 tens makes 100 and 10 100s makes 1,000. Yeah, 1000. 1000 is 1,000. Yeah. And then when we go into the decimals, we go into portions. So now we're thinking about fraction land. This is 1/10. So it would take 10 of these to make a whole because it's been portioned. And this is just 1 out of 10. And then break that, it takes 10. So there are 10 tens and 100. So it would take 10 100ths to create a tenth. So go 1 100th broken into 100 pieces. 10 of these would make one of those. And then 10 1,000ths will make 100th because 10 100 makes 1,000. So 1 1,000th. And then 10 10,000ths would make 1 1,000th. So rebundling, yeah. And what is cool about this is that this actually keeps track of, it's called the base 10 because you see all of these regroupings and by tens. So this is actually 10 to the first power. 10 tens would be 100, so that's 10 squared, 10 by 10. 10 100s makes 1,000, so that's 10 by 10 by 10. So this is 10 tens, this is 10 tens, or 10 cubed, 10 by 10 by 10. So this is just 1, so this is actually no groups of 10. So this we go 10 to the 0 power. And then on the other side, in order to go into portions, we actually say this is 10 to the -1 power. And then similarly, divide by 10 tens to make 1 100th. Divide by 3. So how do I say this? 10 groups of 10 by 10. Yeah, to make 1,000. And then this would be divide by 10 again. So this is just counting up how many times we multiply by 10 or how many times we divide by 10. Okay. So when I think about this and I think about examples of this, let's see, for instance, if we have 4/10, right? And we would put it on here, it would be 4 of these. So that is equal to 0.4, or even 0 wholes 4/10. Yeah. And then when we have something like 2 100ths, which I often think of 2 out of 100, or in terms of money, 2 cents, we would have 0 wholes. We would have 0 tenths because it takes 10 100ths to make a tenth, but we would have 2 of these. So notice that we would have 0 wholes, 0 tenths, and 2 100ths. And then if we said something like 53 1,000th, then what we would see, well, 50 Let's write it. Let's think. If I went like this, let's suppose I think of 5/100ths. Well, that's equivalent. If I chopped all of these into 10 pieces, 5 would be chopped into 50 equal portions, and 100 would be chopped into 1,000. So every piece got chopped into 10 more or equivalents. Yeah, I scaled both the chopping them by 10 each. So this would be 50. So 50 1,000s is equal to 500ths. And now we have 53 of them. So I'm thinking this is like having 50 1,000ths in addition to 3 more 1,000ths. Or, that's 5 100ths. So 0 wholes, 0 1/10ths, but 5 of these, because 50 1,000ths is equivalent to 5 100ths, so 5 in that place, and then 3 of these. So 0.053. I know they're kind of jammed in there on the side of the paper, but okay, so let's look at example 1 where we're starting to compute. Do 0.23 or 2300ths plus 0.607 or 607 1,000ths. Yeah, with fractions. Okay, so this is 0.23 or 2300ths. And this is 0.607 or 607 1,000ths. I'm going to turn these into equivalent fractions by chopping it up. Equivalently, scale it by 10, scale it by 10, making this into 1,000 equal pieces and this also into 1,000 equal pieces. So now they have equal portions, so we can add them. We get, let's see, 837 1,000ths. Okay, and now, or if we're going to rewrite that as a decimal in the 1,000, so 837, so 0.837. Okay, let's do that with decimals. Okay, so if I see 0.23, and I'm going to line up the places. So 0 holes on this one, and also 0 holes on this one as well. So I see 0.607, and I'm going to add. So what I see is that there are no 1,000ths in this part. So if you want, you could put a ghost 0 if you like. Let's see. So this would be 7 in the thousands, 3 in the hundredths, 2/10 plus 6/10 makes 8/10, and 0 holes plus 0 holes makes 0 holes. No carries overs. Did not create a complete hole. Close, but notice how lining up all of the place values also matches the computations with the actual fractions. So let's rewrite this one. So 2 holes, 23 100ths, minus 1 hole, 607 1,000ths. Got it. Let's see. I'm going to write these as equivalencies. I'm going to break this into 100 pieces each whole. That means there's 200 pieces plus 23 more. 223 100ths. And this one, this whole would create 1,000 out of 1,000. So this would be 1,000 and then 607 more. So 1,607 total 1,000ths. And then, these are not equal portions. So I'm going to need to portion this into 1,000ths. Sure, scale it by 10. So everything got put into equal portions now. 1,000ths and 1,000ths. So now all of the cuts are the same, the pieces, and now I can go ahead and subtract. This is when you would, here. 1,607. Right on, it's borrow time. I do not have any here, so I'm gonna go ahead and knock this down to 2, creating 10 of these. 10 take away 7 makes 3, 2 take away none makes 2. Now I'm in the hundreds place. I'm gonna knock down a one of these 1,000s to create 10 100s, so that'll be a 12. 12 take away 12 hundreds, take away 6 hundreds is 600, and 1,000 take away 1,000 is none. Okay, got it. So 623 1,000ths, or written as a decimal, 0.623 would land us in the 1,000ths. And definitely doesn't create a hole. Got it. And if we do this with decimals, let's do that quick. So I'm going to line up the place values carefully. Okay. 6 0 hundredths, but 7 1,000ths. And this has 0 1,000ths, and I subtract. Here comes borrow. And notice how this borrowing is going to be very similar to that borrowing. Okay, this is 3 hundredths. I'm going to take that, knock it to 2 hundredths, borrow one of those. That turns into 10 1,000ths. 10 1,000ths take away 7 1,000ths is 3 1,000ths. 2 hundredths take away 0 hundredths is 2 hundredths. I cannot take away 6 tenths if I only have 2 tenths. So here we go. I'm going to regroup. One of these wholes is going to become 10 tenths. So I have 2 tenths plus 10 tenths makes 12 tenths. 12 tenths take away 6 tenths is 6 tenths. 1 whole take away 1 whole is 0 wholes. And voila. Yes? Okay. So now we compute this. And then I'm going to give you this disclaimer, which is that I am doing this for the benefit of you. Oh man, that's 8 6/10. Because ultimately throughout this entire class, you will actually get to use the calculator for this. So trying to be honest, but I do want to show how it works, even in the event that you're just curious and you're just like, you're doing magic math, made up math. Okay, let's see. If I break 8 wholes into 10 portions, each whole is 10. So there's 8 groups of 10. This would be 80 tenths plus 6 more. So 86 tenths. And when we multiply fractions, we multiply across. I have to do 23 by 86. 23 by 86. All right, here we go. Long saws, but so let's see, 6 by 3 makes 8. 6 groups of 3 makes 18. So there's a 10. 6 groups of 20 makes 120, but plus another 10 makes 130, or 13 tens. 38, okay. 80 by 3 makes 240. So here's that 0, and then this would be 24. Or so there would be 4 in the tens place, and then we would do carry the 2, or really there's a 2 built into here. But I have 80 by 20, and that's 1,600. But then I have 2 additional. So 1,800. Got it. 8 wholes, 7 tens or 70, 900s, and 1,000. Okay. 1,978. 10 groups of 100 is 1,000. Look at that. Oh, so there is a hole. So 1 whole, 978 1,000ths, or 1.978. Okay, that's great. And okay, what's interesting is that if you look back at this, and I'm just going to modify this multiplication in order to do it with decimals. If I put in decimal places, maybe here's blue. The decimal places were here and here. So one of the tricks that most people notice is that, so there were 2 decimal places here that made it the hundredths, and there was 1 decimal place here making it 10. And notice when we multiply the 100 by the 10, we get 1,000. So that's 3 decimal places. And so notice 1, 2, 3 decimal places, but this isn't showing any. So it would really go 1, 2, 3 to get this answer. And you could actually go through and put the decimal places in the right spots here as you go. Let's rank the decimals shown. Okay, use fractions, then decimals. Okay, so this is 32 hundredths. This is 32,032 thousandths, 32 1,000ths. This is 237 1,000ths, 237 1,000ths. And this is 1 whole and 2/10, 1 and 2/10. Okay, right off the bat, I noticed that this is the biggest one because it has a hole and these do not, but they don't have equal pieces, which is kind of like hard to compare. These two do. Look, this has 237 out of 1,000 pieces, and this one has 32 out of 1,000. So this one is clearly bigger. So let's make this one out of 1,000 pieces. Scale it by 10, makes 320. So this is actually bigger than either one of these. Okay, so here's what I see. We need it from smallest to biggest. So this is the smallest. This would be the second because it's 237 of them, and this one was 320 of them, making this the third. And then this would have a complete whole, which by the way would be 1,000 1,000ths, which is more than either any of these. So this is the biggest. Okay, so now what I'm going to write them down is, okay, so here's what I see. The smallest was 0.0 and 32 1,000ths. Next was 0.237, 237 1,000ths. And then this one, 0.32 or 32 100ths, and then 1.2. Whoops. Many people look at these places and say, okay, start from the left. Wholes are always bigger than tenths, which makes sense because whole dollars are more than a dime. And it takes 10 dimes to make one of these. So they always say, start from the left and work to the right. So this one is the biggest because it had a hole. But then, so now once that's done, now look at these and you look at the place value to the left. This one had 3/10, only 2, and only 0. So making this one bigger than the others because this only had 2/10 and this had 3/10, which are more 10 times bigger than 100th. So remember, like this is dimes, 2 dimes, 3 dimes, and this would be pennies, 2 pennies, 3 pennies. So always look from the left to the right in terms of just using the decimals. Okay, couple of remarks. Why do we love decimals, or why were they created? Decimals were created for a convenient way I definitely feel like I misspelled that. There's no I here. Convenient. There we go. Convenient way to compare fractions. So here's what I mean. Looking back at this problem, ranking these, if we just have this little trick of going left to right to rank decimals, when we look at fractions, I mean, we had to cut them into equal pieces in order to be able to compare them. Like we couldn't really compare 32 hundredths to 237 thousandths because they were in different portions. So decimals were really created for a convenient way to quickly compare fractions. And then shortcuts for decimal arithmetic are founded in fraction operations. So if you're ever thinking, why do those decimal or shortcuts work? It's all because of how it ended up happening with the fractions themselves, like 2 decimals, 1 decimal, 10 hundredths is 1,000th. So that's why. Another thing that I feel like is remarkable is that most people forget the decimal shortcuts. So most people forget decimal shortcuts because they are confused about why they work, or they forget why they work. And usually when you don't, when it doesn't quite stick and you're like, what? You kind of just like forget about it. So there you have it, right? So most people forget decimal shortcuts because they are confused about why they work. Comparisons are made a bit easier using percentages, which is why this section is about percentages. So if you're ever like, why do we even do this? It's because let's do some comparisons. Let's look at this. Okay. Percent. What does it mean? The part per means out of. And cent means 100, like century, cents in a dollar. So percent means how much out of 100. Yeah. So let's translate the following. 86%. 86 out of 100 portions. Then write it as a decimal. Well, this is 0.86, 8 tenths, 6 hundredths, 86 hundredths. 7%, 7 out of 100. Well, there's no tenths. So 0 tenths, 7 hundredths place. Ooh, now this one's weird. This is a portion of a percent. So this is 0.04 out of 100. That's strange. So let's scale up, scale up. Let's scale up by 100. Just to make, so I'm cutting all of these into 100 pieces because this is in hundredths. 100 hundreds. Well, 10 hundreds would make 1,000. So 10 more would make 10,000. Got it. And 4 hundredths by 100. So 100 of these would make 400 hundredths, or just 4. Okay. I'm fine with that. You could simplify it if you want to. They're clearly both divisible by 2. First, I'm going to write it as a percentage, or I'm sorry, as a decimal. We wrote it as a fraction. I want to write it as a decimal, especially because it's in the 10 thousandths, which is part of, let's see, we would have to look back. And this is 1,000, but then 10,000. No, here we go. There's the 10 thousandths. So it'd be 0.0004, or, okay, 0 tenths, 0 hundredths, 0 thousandths, 4 1,000ths. Now, just for fun, I am going to go ahead and simplify this. Scale it down by 2, we get 2. Scale this down by 2, that would be 5,000. Okay, now these are both divisible by 2 as well. That would be 1, and this would be 2,500. Okay, so if you want to write it as a simplified fraction, there you go. And there it is as a decimal. Let's deal with this 12.5%. I immediately just turn that into a decimal and then put 12.5 out of 100, scale up by 100, 125, 1,000 of those, equivalent fraction. And then I can write it as a decimal, tenths, hundredths, thousandths, tenths, hundredths, 1,000ths. Okay, and you can simplify this if you want to. And now 200% would be 200 out of 100. And that actually is 2 wholes. And that is its decimal and fraction. Let's go ahead and write each decimal as a fraction, then as a percent. So this would be 1/10, which is equal to 10 100ths. And I did that, so it would be out of 100, or 10%. Here, so just so that I'm crystal clear, I scaled this by 10 and scaled this by 10, chopping them into further and further pieces to get it out of 100. This one is tenths, hundredths, so this is 5 100ths. This is even easier. 5 out of 100 makes this 5%. Okay. And then 1.23 is 1 whole 23 100ths, but that would be 100 100ths, so 123 100ths, or 123%. So this is a whole 100% plus 23%. Yeah, I like to think of it that way. A whole 100% plus 23%. And now this is not, because there's nothing out of 100 here. So what is this? 2 tenths, hundredths, thousandths. So I'm going to actually have to scale this down and divide by 10 to make that 1,100. So if I have to scale that down, so this will be 100, so that's good because then it'll be out of 100. But this 2 tenths is 0.2. So as a percentage, this is 0.2%. Okay, so most people remember the trick. Some people forget it, like I mentioned in that comment about most people forget decimal shortcuts because they're confused. But most people, when they're going from a decimal to a percent, remember to multiply by 100 because it's out of 100. And so they go boop, boop, 0.2%, boop, boop, 123%. Move it twice because that's multiplied by 100, 5%. Multiply this by 100, boop, boop, 10%. Okay, so that's legit. A campus has 10,000 students and 22% of them smoke. How many students smoke? Well, this is 22 out of 100. So, okay, but this is 10,000. So, let's scale up by 10. That makes it, that only makes it 1,000. So hold on. That would be 220 out of 1,000, but this is out of 10,000. So let's scale up again. going green. Let's see, 2,200 and 2,200, and this would be 10,000. There. Campus has this many, 22% of them. How many students smoke? 2,220 of them. Okay, now another way to do this is change this into a decimal. So 0.22 of, which is multiply. So 22% of the 10,000. Okay, well, what this does is move the decimal place 1, 2, 3, 4 decimals to the right, making larger. So 1, 2, 3, 4. 2,200. Oopsie. 2,200. Yeah. So it is nice. This was using equivalent fractions. This was using multiplication, but I had to convert it into decimal form in order for that to work. Because if you did 22 times 10,000, well, that would be 220,000 students, but there's only 10,000 students. So there's not even enough students for that to even happen. So you need to make sure that when you're doing a multiplication, if you're going to do that, to convert it into the decimal form first. Let's say there are two kinds of meat at a store. First package says 1 pound has 1/10 fat. Other pound has 2/25. Which of these has less fat in it? Well, I see 1/10 and 2/25, and these are actually challenging for me to compare. So I am going to convert them both into a percentage. Here we go. 1/10 is equal to 10 100ths by scaling up by 10. That one is 10%. Let's see if I can make this out of 100. Well, this is 2 out of 25. If I multiply 25 by 4, 4 quarters makes $1. So 4 groups of 25 is 100. That's what my goal was. And this would be 8. So this is 8% fat. So here's what I see. This one is the 10% fat. This one is the 8% fat. Or you could look at it as 90% lean and 92% lean, however you want to say it. But which of these has less fat in it? This one. That one has less fat in it because it's only 8% compared to 10%. Jeremiah's annual income just increased from 20,000 to 30,000. Talia's income increased from 160,000 to 170,000. Do you think that one of these individuals feel the increase more than the other? I do. I feel like if someone starts at 160 grand and goes to 170 grand, they don't feel it very much. But if someone is living off of 20 grand, which happens, I've been there, and they get an increase to 30 grand, that is a really big game changer. Okay, so does one individual feel the increase more? Yes, because this person, Jeremiah, is desperate for cash, but Talia is not. She's living large. So I definitely think that Jeremiah feels it more. Has a bigger life impact. Right? Was the increase more? No. From 20 grand to 30 grand, that was just $10,000 increase. I mean, not just, that's a pretty big increase. So was Talia's. So we can't just think of it as raw dollar, because Jeremiah's definitely has a bigger impact. Okay. So that's where percentages come into play again. We have this thing called percent change or percent difference or relative change. Which one is relative? And that is equal to this formula, the end amount minus the beginning amount, short, I'm going to say begin amount, out of or compared to, as a ratio to, the begin amount comparing to, and we multiply that, we scale it up by 100 to turn it into a percent. Check about that. There are times when this formula will show up looking a little different. Like maybe they would say the new amount compared to the original, but then we need to compare that to the original. So there are different ways that people explain this formula, but ultimately you want to keep these two in the correct spots in order to know what you're comparing it to. Because this denominator tells us what we're comparing it to as the original. So in terms of this formula, order matters and the sign. So let me just remark that order dictates the sign of percent change. So order matters. It matters. Okay, and the denominator shows what it is compared to in the ratio out of the begin amount, so or begin amount. So that means we're comparing it to the original. All right, example 3, enrollment. Use the data in order to answer these questions. There's a data source here. So I'm looking at this. Let me just give a quick scan. I see through the years from 2007 to 2011, there's a raw head count of fall enrollment, and there's also a percent change. So, first thing I notice is that some of them are positive and some of them are negative. FTE is full-time enrollment because, as you know, at community college, we got some part-time, we got people taking leisure classes, we got part-time, we got full-time, all kinds of different students. And then the percent change of that. So this is all count versus full-time students. Okay, let's get to it. What was the change in enrollment or headcount from 2007 to 2008? This just says change. So when I think about change, it does not say percent change. So that means we are doing this is the change, the end amount minus how it began. So let's see. This is what it was in 2008. 357,157. And this is what it began as. So find the difference between that and 347,277. Okay. And if you compute this, you will get 9,880. And if you think I'm magical, no, either line up the place values and do your borrowing or use a calculator. So that is the change. Write what this number means in terms of the situation. Okay, so the head count. Okay, and now I'm thinking it's positive. Did it increase or decrease, right? Well, it increased. Because I took 2008 and subtracted 2007 and that number was positive, it means it was higher in 2008, indicating an increase. So positive here, the head count increased by 9,880 students from 2007 to 2008. Okay, so order matters. So when I said order dictates the sign, rearranging, flip-flopping these would have turned out to be a negative 9,880. And that means that this is below that one. So we need to kind of think of it as the end amount or new amount, take away the original when we're doing that. What was the percent change in enrollment? So now look, this says percent change, which means I actually need to do a comparison to the original amount. Okay, so let's see. End amount minus begin amount, end amount in 2008 minus the original amount in 2007. And then I'm going to compare that to, so the new amount 2008 minus how many full-time students in 2007, and compare that to the number in 2007, the original. So 347,277 students originally in 2007. And then scale that up by 100 to turn it into a percent or out of 100. Okay, so what would that be? So subtract this and we get the 9,880 that we saw in this. That's the change. Compare that to the original amount in 2007 and multiply by 100. This is calculator work if I ever did see anything. So just so you know, I punched that into the calculator and here's what I got. 2.84%. Actually, here I'm going to get out my trusty old calculator. Let's double check, because sometimes even, you know, after all of these years of doing math, I still make mistakes for sure. Okay. And notice it says 0.0284499. Oh, I didn't multiply by 100 to make it into a percent. So here it is before percentage, multiply by 100, turn my decimal into a percent, 2.84. And because this was 4, I did not round up. Okay. So explain what you computed in the context of this situation. Okay. The head count, and because it's positive, it still is an increase. The head count increased by 2.84% from what it was in 2007. So I wrote down what it was going to be, what it was compared to the begin amount. Okay. So it increased by 2.84 from what it was in 2007. Was the full-time enrollment lower or higher than 197,473 in 2006? Well, look, we do not have 2006. That would be like right here, right? It's not, we do not have that data. So we must have some way to think about it. Let's see. Well, we're looking at full time. And here's that number. So this is the 2007 amount. So let's see. We do have a percent change in full time. So I'm kind of looking right here. So if we were to compare it to 2006, and it was a positive percent change from 2006 to 2000. Let's write that down. There was a positive percent change of 0.3% from 2006 to 2007, or from what it from, I don't like what. Let's go from the full-time enrollment, the full-time enrollment in 2006. Okay, so if there was a positive change from 2006 to 2007, that means there had to have been fewer students in 2006. Was the full-time enrollment lower or higher in 2006? So 2006 lower, 2007 it had a positive percent increase or a growth. So that means this is higher enrollment. Okay, and that gives us our answer. So, so just to make sure we're crystal clear here, right? A decrease in enrollment would be given by a negative percent change. Yeah. Okay. So because this was positive, that means from 2006 to 2007, there was growth in how many full-time students there were. Quick summary. Let's look back to the beginning. Okay. So in this section, we converted between fractions, decimals, and percentages because they're really just several ways to represent equal values. So this is yet another way to do equivalencies. And we computed and interpret percentages and percent change in the context of an actual situation in reality. Okay, overall, what I want you to get is that because we have 10 digits, we based our system on counting by tens and groups of tens. And then we used a decimal to indicate the difference between wholes and portions, because we like to do that too in life. And ultimately, these percentages are so nice because they allow for things like quick comparisons, such as when we look at this and we're like, oh, 10% versus 8%. Ah, I know that this one's bigger. And so really at the rub is that we evolved. You know, we love our portions, we love our fractions, they're the foundation. And then we said, you know what, let's convert those into keeping track of portions. And then, you know what, we like whole numbers. So let's suppose for fun, when we have these portions, we put it out of 100 so they look more like whole numbers. So there's percentages. Lovely, lovely percentages.